So welcome everyone to the SGA meetup, this time on the topic of optimizing energy efficiency in Unity with Dale Kim today. So today we will talk about energy savings by utilizing SIMD instructions with Burst and Unity.Mathematics. We have 1 hour, and after a short intro by me, I will hand over to Dale Kim, who is a software engineer at Unity, who will, give us a presentation on his best practices. And then we will have an expert discussion, which will be led by Neil Patel, who is VP of Sustainability at Take-Two. Afterwards, we have still time for an open Q&A. So if you have questions, just drop them into the chat, and at the end, we will address those. Who am I? I'm Maria Wagner. I'm the managing director and one of the founders of the Sustainable Games Alliance. Our mission is to decarbonize the games industry, but also supporting the games industry with using resources more efficiently, also energy. That's why we organize knowledge sharing meetups like this and also develop different kinds of tools which help developers to use resources more efficiently. Here you see all of our current members. We also have a bunch of supporters. If you like to support us, just reach out. This meetup is a energy efficiency network meetup. This is a network of global, basically developers, a global network, and they develop different tools which help to save energy efficiency and share knowledge. One of the latest tools this network developed were different energy saving plugins for Unreal, Unity, and Godot. And actually, one of the makers of the power saving plugin for Unity is here with us today. It's Oliver Stock. You will hear from him later on more. And actually, we will also have a meetup specifically on this topic later in May. I will post a link on that later. So, now I would hand over to Dale, but before doing that, I will quickly introduce him. So, as said, Dale Kim is a software engineer at Unity. There he focuses on improving the performance and scalability of Unity's job system. So he's perfect, to give this presentation today. I met Dale at Unite in Barcelona last year. And was really, I really liked his presentation. So I invited him to share his knowledge and best practices with our community. So thank you, Dale. Neil, who will lead the expert discussion, is over 5 years at Take-Two and has a background in sustainability and ESG reporting. So he's very much familiar with why energy efficiency is also important for the environment and the player experience. Then we also have David Zapfe-Wildemann with us, who's the co-founder and director at neoludic Games. They released Tiny Bookshop, which was very successful, and besides being very successful, it is also quite energy efficient. So that's why we have David with us today. And last but not least, Oliver Stock. I quickly already gave an intro on him. He is the co-founder of Walk the Frog and one of the developers of the power saving plugins. And now I would hand over to Dale.
Awesome. Thanks, Maria. It's great to see that there are people who care about this. So let me go ahead and get the presentation set up.
Yeah.
All right. In theory, this is now going full screen. Okay,
Yes.
perfect. Hello, everyone. Welcome to my talk, CPU energy efficiency, the race to sleep. If this is familiar to any of you, it's because I gave this talk at Unite last year. So if you've already seen it, Sorry, but we'll have a healthy discussion afterwards. So hopefully you can get some more information out. First of all, who am I? I'm Dale Kim. I'm a senior software engineer at Unity. I work on the kernel team where we're responsible for a lot of low-level stuff, lots of stuff with dots, entities, packages, collections, and in my case, the job system, the performance of the job system, scalability of the job system, all that sort of stuff. I generally care a lot about low-level CPU performance, so I spend a lot of time looking at like atomics, memory ordering, how does the cache work, and why it's making things slower and not faster, stuff like that. And I also happen to dabble a little bit in math, but that's a separate thing. So what is this talk about? This talk is about achieving better energy efficiency through higher performance by using all of the hardware that you have. There's lots of hardware that's out there, and most of the time you're not using all of it. So we want to use all of it. Um, One of the key ideas that I want to get across is this thing called the race to sleep. It's really important in energy efficiency. It's sort of like the main thing that happens to get energy savings. We're then going to talk a little bit about what the hardware actually is capable of, and this idea of scalar code versus vector code. And then finally, we're going to go through a high-level walkthrough of hand vectorizing code using the Burst package and Unity.Mathematics. So let's get started. What is the race to sleep? The race to sleep is sort of this screenshot, which you won't understand yet, but this is a profiler capture of, it's just some random thing that I was working on, and I'm looking at the idle time of the threads. And if you decide to add up all the idle times, what you'll notice is that actually it's like about 18 and a half milliseconds. So that's a number, right? And then I optimized things in this game, and I take another profile capture. I look at the idle time again, and this time instead of 18 milliseconds, it's 53 milliseconds. So we're going idle for a lot longer, right? So how is that the race to sleep? Well, the faster you finish your work, the sooner that you can go to sleep. In this case, we're talking about the threads that you schedule for your process with the operating system. So if you go to sleep, the operating system has a chance to schedule you out, do other work that's more important, or maybe turn off the CPU completely. If it's off, that's like the ultimate energy savings. So the faster you do your stuff, the sooner you can put your thread to sleep, the sooner that, you can give up your time, save energy. Okay. That's the key idea. And so if just going back a little bit, the hyperscalers of the world, they're doing this all the time, right? They're like, oh my God, we have these data centers and we want to save 1% energy so we can save a few $1 million on electricity. It's exactly the same, right? So we want to do that, but for our games. So we're going to move on to what the hardware actually can do. We're going to start off with this idea of scalar code. Scalar in this instance is referring to just one value. Right now, we're stealing a term from mathematics, scalar being just one thing. What we're going to do is we're going to take registers containing scalars, one value, and we're going to do an operation, and that operation is going to take the inputs and then generate one new output, right? It's all scalar, so we have two vector registers with A and B. You want to do an add, and then at the end, you get one new value, A plus B, right? And this is sort of the tried and true mental model that almost every programmer is aware of. That's how they learned programming. It's very intuitive, and you have to painstakingly tell the CPU how to do one thing at a time, right? That's sort of programming. So let's go look over visually what the scalar execution looks like, which will help us understand what vectorized execution is like. In scalar execution, in this example, what we're going to do is we're going to take an array with 8 values in it, and we're going to increment every single element. That's all we're doing, right? So this is a very typical loop where you look at all the elements. And the important thing about this to notice is that in the loop, we're doing this thing where it's like, oh, for the index, add 1 every single time. And then in the loop body, do the work that we care about, which is add 1 to whichever element we're looking at, right? So it's very, very intuitive. All of us have probably done this, right? And so for us to complete this work of incrementing everything, there's going to be 8 invocations of the loop body. You have to loop 8 times. And every time there's going to be a load, an add, and a store. So you do all these things 8 times, right? That's, pretty typical of scalar execution. But then what's the alternative? The alternative is this thing called vectorized execution, also known as single instruction, multiple data. I like to say SIMD. Um, in this case, vector is referring to multiple values. We're again stealing a term from mathematics, but this is not the same as a mathematical vector where you can like normalize it. And we're not talking about that vector. We're talking multiple values. Um, what are the multiple values? In the register, you can actually hold multiple values, in this case, 4 values. And I'm showing 2 vector registers here on the right, where one vector register contains only A's, and then another vector register contains only B's. And what we want to do is we want to add these 2 vector registers together. And that addition is actually component-wise, so vertically in this diagram. So you get A0 plus B0 as your result, but you do it for all 4 elements at the same time. Because all of it's happening at the same time, and it takes as much time as the scalar code does, you're doing 2 times more work, 4 times more work. So you can be 2, 4, 8, 16 times faster, depending on how big this register is and how many elements it contains. Um, this can also lead to more bandwidth efficiency because of the techniques required for you to get to the point where you can do the vector processing. But we're not really going to go into that in this presentation, but this is often a huge benefit. And so the thing I want to get across is that if you want to be the most efficient on your hardware, you really need to be using vector instructions because it's the only way to use all the hardware, all the silicon that the hardware designers baked into the processor. If you're not using it, you're lighting up the processor and not using all the units and going slower than you can. So you actually need to be using these instructions to be the most efficient that you can possibly be. So what does vector execution even look like? We're going to go back to our incrementing example. We're going to have the same array of 8 values, and we want to increment every single element. First difference that you want to look at is actually here, this line at the very beginning, we have this new variable called ones in blue, and this thing is an int4. It contains these 4 values, and we're initializing every element to be 1. This serves as sort of like the constant in the previous code that we just said plus equals 1. That's sort of serving as this, but now we manually have to fill out every single element has ones. And now the loop condition has changed. The loop condition used to be just I plus plus I incremented by 1. But now we are manually saying in this code, I'm going to process 4 items at once. So you got to increment I by 4. And then in the loop body, you'll see that in this code, it might look a little weird. Like I'm like extracting out, the first value, the second value, third and fourth value manually. You would think, oh, there's 4 loads here. Because we're using Burst and Unity.Mathematics, Burst knows what this really is. And it can actually just be 1 load. So this is just 1 load, but we're actually loading the first 4 items into this variable. And then we say, oh, take that variable, add the ones we're incrementing. And then we store the values back, right? So when you go through one loop iteration, we're saying +1 to these 4 elements. And then in the second iteration, we're looking at these last 4 elements. We do the same thing. And so in this particular case, we've only done 2 invocations of the loop body, where the loop body each time does 1 load, 1 add, and 1 store to process 4 items. And so now that actually gets us 4 times the throughput. We're 4 times faster in this code compared to the scalar version, right? So that's like the power. That's in essence, the power of vectorized execution. So let's take that idea and try to do it in a more realistic example, okay? So this is a link to a GitHub repository that uses entities, and it's a sample that Unity created to sort of illustrate, the kinds of things that you might want to do and how you might want to do it. And it's called ECS Galaxy sample, and it's like a big spaceship sim game where you've got thousands of ships and they're all swarming to like take a planet basically, and they'll do combat. You can look at this branch where I will go through all of the optimizations that I'm actually presenting here, but you can actually look at the code, pick it apart, and do all the things. There is kind of a lot of code, but we're not going to focus on the actual little bitty details. We're going to stay high level. So try to resist wanting to nitpick at every single piece of code on the slide. You don't really need to know everything. We're just going to look at the high level stuff. So the first step, you want to profile, always profile. I profiled that sample and, looking at what's taking up all the time. The time that is spent is usually energy being spent. So I look at this profile capture and I see that there's this thing called fighter AI job. And it's quite large. In this case, 64 milliseconds in 1 frame. So this seems really promising. Once I found that in the Unity profiler, I decided to go into a native profiler to be like, where in the code really is it spending time? And the native profiler showed me this result where there's a loop. And on each line of the loop, there's like all these percentages, which tells me percentage of time being spent on approximately all those lines. And it's 68% in this example. So this loop takes most of the time. This is really promising. So then I keep looking and digging further into the code. So what is this code actually doing? Um, well, the main thing is it's a loop over this thing. It looks like an array, right? Um, you always want to start with the data that you touch in your loops. This will give you an idea of what is possible and which data is sort of the important stuff. And in this case, the important stuff looks like it's the fighter action. It's used in almost every single line of this loop, so it seems pretty important. What is the general gist of this loop? It looks like it's, getting the fighter action, calculating some proximity, some sort of importance. It does it for every single fighter action. And then it does a conditional to do something with what it computed, right? It's got to remember something. So the loop itself isn't all that complicated, right? But it looks at the fighter action every single time. What is it fighter action at all, right? Let's look at what the fighter action is. This struct fighter action is just the struct full of data. It has entity, has position, has a radius, and has this thing called importance. And I've also colored each of these data members. Each of these colors corresponds to this diagram here. This diagram is showing a high-level memory map of what an array of these fighter actions would look like in memory, right? So here we have the first fighter action. Here we have the second fighter action. And if you want to get to, say, the entity of the first fighter action, you're going to this cyan right here. If you want to get to the entity of the next action, you have to jump in memory all the way to here, and this is your next one, right? So this is sort of how these fighter actions are laid out in memory, okay? Really important diagram here. This has a name. It's also called an array of structs, AOS. It is exactly what it says. It is an array of fighter actions, the struct, right? So how do we go from here, which is what the code currently does, to here, which is what the hardware can do, right? You're looking at these side by side, right? What we want is to mirror this setup here, where each register sort of has the same type, the same color. If I say load this cyan here, well, I might get cyan in like the first or the second element, but then it's going to suddenly turn purple, right? I don't want that. I want it all to be cyan. So does that mean I load each one individually? No, that also is going to, that's probably going to be slower. This data layout just doesn't match. You don't want this. You actually want something different. Imagine a world where you had arrays full of all the cyans, full of all the purples. In this case, that means an array of all the entities, an array of only the positions. If you had that, what you could do is say, load me a vector register full of the entities, and you will get only the entities, right? That's the idea. That's what we want to achieve. This diagram in the middle also has a name. It is called structure of arrays. We've sort of flipped the two around. And so it is kind of spoiling what we actually need to do. We need to create a new structure. In this case, we're going to call it fighter action SOA, which contains a struct. This is a struct full of arrays. These are unsafe lists. They're just arrays. And now we have all of these arrays in it. And these first two are cyan also. These two cyan arrays correspond logically to this entity right here, this data member. Why are there two versus one? Well, if you look inside entity and look at the definition, it turns out it has two ints in it. And we really want to have fundamental types of these arrays. So because it has two ints, we have to sort of expand it into two separate arrays, one for the index and one for the version. And it's the same thing with the positions. Positions were a float 3 with x, y, z. For us to get truly homogeneous data, we want all the x positions in one array, all the y positions in one array. So now we have 3 arrays for this position. So this is a really important arrangement for doing SIMD. How do we actually do it? Well, it turns out most of the work is in actually achieving this structure of arrays format. Once you have this, it's very, very easy for you to use Burst and Unity Mathematics to just do the vector processing yourself. And that's exactly what we're about to do. So here is the vector code of the vectorized version of the previous code that we were just looking at. There's a lot of text, too much code, font's too small. We're going to split this up. We're going to do the top half first and then the bottom half. Here's the top half. So the first thing to recognize is this loop condition. If you remember what it used to look like, it used to be like we always done, plus plus I, increment one at a time. We've changed it. This loop now says, hey, we're processing 4 items at a time. While there are 4 items to process at a time, go do the 4 items. And then once you're done with the 4 items, increment by 4. So you work on the next 4. That's all this loop condition says. And then inside the loop body, um, this looks a little different, but is in essence the same. The previous code would say, get me the fighter action position, extract that out, and then we're going to send it to a function to do things. But now what we're doing is saying, let's grab out positions for 4 fighter actions at once. That's why it's, I plus 1, I plus 2, I plus 3. And we do that for all the X, Y, and Zs. Now we have float 4s, 3 of them to contain the full float 3 position for 4 fighter actions all at once in this one execution of the loop body. We also grab out the fighter action importances, and then we send it to this other function. I've now created this new version, an SOA version of this function. Let's go look at that function. Here I actually have the original code on top and the new code on the bottom that does 4 at a time. The old code did 1 thing at a time. These 2 pieces of code are identical. They produce exactly the same values, but one of them does it 4 at a time. And if you dig through the code, you can convince yourself this is actually the same. Same with this orange box, also doing exactly the same thing. Here's a 1 minus the saturate. Here there's a float 4 of all ones minus saturate, which is also going to be a float 4. So it does it for all 4 items at once. And same with this, return result. And the code even looks almost identical, but it's just now we're doing it with 4 at a time, right? These are the same. Because we're doing 4 at a time and everything lines up, we can then continue to use float 4s, do our computation, and store the results so that way, we've computed what we need to compute. The bottom half is a little bit more interesting. The bottom half now has this much bigger section of code, and you're kind of going, wait, is it really the same? What are we doing, right? Look at the highlighted parts. This top code is the original code that we had in Scalar. And this original code said, if the current action's importance is negative, and if the entity matches my target, then remember this importance, right? This code is doing the same thing. If the current action importance is negative, then check to see. Well, first we load up all the entity IDs, all the entity indices and the versions for 4 of them at once. And then we compare for all 4 of them, is it matching my target? If it is, then we're going to have this bool 4 that says the result of all those comparisons. And then if any of them matched, if any of them had this same target entity, then we have to do this new section of code. Why is this new section of code necessary? It's because this original code is doing one thing at a time and then sort of remembers the first non-negative result. I need to achieve the exact same semantics, but now I'm doing 4 things at a time. Okay, how do I deal with this? Well, I'm just saying, well, if any of them match the target entity and we're already negative, just go in order X, Y, Z. Whichever one is the first one that that matched, that's the action of importance that we're going to remember. So that way we maintain the same logic as this original scalar code. Okay. Sometimes you have to do lots of things like that to make sure that the meaning is exactly the same when you do your translation. So now, assuming you do all of this and all of your code compiles and all the code is correct, you can then go run the code and profile again. And in this case, before I was spending 64 milliseconds for the whole frame, and then after this optimization, it's 38 milliseconds. A lot less time is being spent to compute the exact same result. And if you go into the Unity's profile analyzer package, you can see all the data in a more convenient way, right? I have a speed up now of 2.29x for this specific piece of code. And if you actually look at the idle time, the idle time is now increased too. It is doubled almost. We're now idling 28 milliseconds more, but we're doing the exact same amount of work. That is energy efficient. So, you know, this is all in the Unity profiler, and like I know intuitively through my experience that this is going to be energy savings. But is it really? So I went into a native profiler, deployed this code to my phone, and then measured through the profiler how much battery is being used. And before, if someone were playing the sample for an hour, they would use about 53% of their battery. And then after this one optimization, it's 48%. So if they play for 1 hour, I will end up with approximately 52% battery, not 47, So I've saved up like 4 or 5%. Um, so that's sort of like the gist of how all of this works. So what do you want to do? Well, if you want to save energy, you actually just want to be faster. You want to do your work quicker. And the faster you can do your work and go to sleep, the more energy that you can save. Um, in this example, we were using Burst and Unity.Mathematics as a sort of a cross-platform vector SIMD library. You can choose to opt in and do this yourself because often the compiler can't do it. And this is usually the way that you end up having to do it. Um, Vector code is often a huge boost for doing mostly a mechanical transform. You just sort of need all the data in the right arrangement so that way you can get the CPU to go do the thing it can do. Again, you have to have your data in the right layout. If it's not in the right layout, it's really going to be hard. So a lot of the effort is spent in figuring out how do you get all your data into these uniform arrays so that the CPU can just process all of them, right? But if you can do this, you can get huge gains. You're always thinking about like what is the data layout. You're not really thinking about what is the CPU really doing. You're mostly thinking about what is the data layout, so that way the CPU can do the thing it already knows how to do, right? So that's the end of my talk. Thank you so much. Hopefully it's useful. Yeah,
Thank you
that's
so
it.
much, Dale. Awesome. I really.
Oh, perhaps I should keep the slides up if someone wants to refer to them.
Yeah.
Let
Neil, do
me.
you want
Yep,
to? Yeah.
sure. I'd happy to. Dale, that was awesome. Really appreciate you walking us through it and having great examples. I think from there, Oliver and David, of course, jump in with some follow-up questions as we go. But the first question I had
Oh,
is, just following up on your example, you use one with just four steps or four pieces of data. Are there any limiting factors to the array size or any kind of diminishing returns as you
sure.
kind of develop?
Yeah, so this technique does have a few limitations, mostly like if you know that you only have like one item or two items, like a small number, this is not likely to be all that useful. This optimization is really sort of like what you do after you've achieved your algorithmic gains. So, if you know that you have like a quadratic algorithm, probably need to address the quadratic algorithm first. But
Mhm.
if you've done all of that and you're like, oh, I still have like 500, 600 items, that's a pretty chunky piece of work. If you have at least the number of items in your SIMD register, usually that's worth it. But then there's like practical engineering costs. But yeah, as long as you have at least like dozens of items, the SIMD is usually going to still win. Um, Always choose it as sort of a last resort. Like, oh, I just need to blast through all of this data. That's, I got a lot of it. I can make it uniform. Then SIMD is great. If you have lots of data that's not uniform, say like there's lots of conditional logic that's in your loop. Like the loop in there that I had, there was just one conditional in there, and the conditional was super simple. But if you have like really complicated, like, I don't know, you have some sort of RPG and you have special effects that like someone's got a buff and all these weird conditional logic, that might not be a good match for SIMD because you really want uniform pieces of data. If you don't have that, SIMD becomes a lot harder. So in those cases, I would probably tend not to go for doing the SIMD processing because there's just not enough uniformity for you to really leverage the CPU's power.
Okay, that makes sense. And then I guess following up, from the non-developer perspective, it seems like it could be a lot of work to kind of rewrite the code base. What would you recommend them being like the first step in going down this path?
Uh, the first step, honestly, in Unity is like if you are not using Burst, you probably should. Unfortunately, like a lot of people will still use managed code, so like garbage collected stuff, and that prevents Burst from being able to be used. But if you can do it, Burst gives you huge gains right off the bat. Sometimes it's 10 times faster because all of it's compiled and there's no garbage collection. So that really would be the first place I would start. Um, because any performance improvement, like I said, this is the race to sleep. Anything that makes your code faster is going to get you energy savings. So do the compile with Burst, get everything to be machine compiled, avoid
Mhm.
garbage collection. And after that, it's probably algorithms. And for me personally, for most people, I think they probably need to start with like jobifying parallelizing first. Usually parallelizing, if they can use like the Unity job system, it forces you to get in a position where then you can just do SIMD processing if you really want to. Um, but yeah, I would say it's really dependent. Go look for like pieces of code where you know you're doing lots of stuff. Like I'm
Right.
processing all the sprites of my game or something like that. Something graphics related tends to be a good place to look at where you have huge bulk processing of data.
Okay. Got it. So basically what you're saying is you can take advantage of this step without, being an expert in CPU, like the structure or the infrastructure.
Yeah, you don't really need to. You just need to understand the core idea of Unity mathematics with component-wise operations. Like I said, like if you put two float four sort of vertically stacked on top of each other and just imagine you're doing vertically the operation that you're talking about, if you can see things that way, that really gets you sort of most of the way there. If you have independent pieces of work, SIMD will naturally fall out of that.
Mhm.
So if really the hard parts are where there's lots of logic in between the data, that is legitimately challenging. In those cases, you tend to have to do more high level optimizations. So like in your game, say like, if I have to do this conditional check, is there a way to group all the data to be like say this one's dead, this one's alive. If you can just say instead of checking each one, is it alive or is it dead, can you have an array of all the dead items and all the live items? If you have that separation, that is really going to prep you for being able to do SIMD. That sort of stuff helps out a lot.
Right. Okay. No, that makes sense. And then if we think about like as a team working on this, what are the challenges from addressing that complexity and like debugging from that
Right.
perspective?
So one of the things that's pretty common is a lot of people, because this is not familiar to them, they're wanting to get started and it's like daunting and really it's you do have to spend some time
Hmm.
so I would say for honestly a lot for most teams I would say jump in the sample that I linked in the presentation because you can play with it. It's a straightforward application of this optimization and I think it needs to be that the programmers do need to spend some time getting used to this idea. Once you do it and you understand it, it's actually pretty straightforward. But I don't know of any way to sort of jump in and get these results quickly. You do need to invest some time to learn it and be able to see where it can be applied. A lot of people, what they'll say stuff is, well, the compiler can do this, right? And actually, no, the compiler can't really do this. Most logic is too complicated for the compiler to do it. So it really is sort of up to the programmer to know. The programmer is the one that's in charge of all the data relationships. So really understanding your data really well, like get the programmers to really think about how this works. You might want to have a more senior programmer to help educate the junior programmers. But I actually think that most people can learn this. It's just the challenging part is doing it under time pressure. A lot of people will
Yeah.
say, I have bigger fish to fry, and that can often be true. Because you do have to change so much of the data layout, it often is better. So for example, here I'm talking about CPU performance.
Hmm.
It might actually be better for you as a team for you to say, let me look at the GPU. The GPU just hogs so much power. If you can like reduce the frame rate, that can be like the biggest, simplest win right there. So
Yeah,
I'm kind of under,
that's the
Yeah.
paradox, right? Sometimes it's good for the CPU to be the bottleneck because it's actually drawing less
right.
power.
And so I'm gonna undercut myself a little bit. Like for most teams, I'm guessing that actually they need to be looking at the GPU, but the principles are all the same. Can you execute this code less frequently, or can you do it more efficiently? And so for a lot of teams, it might be more practical to focus on the GPU because it's really easy to scale that up and down. Down res the thing, slower, lower frame rate. With CPU, you're like depending on the calculations. So it's really, really, you have to know your own code very well. You have to know where those
Right.
optimization opportunities lie.
Right. And I think you pointed out, time crunch, time sensitivity, I assume affects all teams.
Yep.
Do you have any kind of guidance or tips on what else, our developers could say to what we can say like the naysayers or the ones that are hesitant to move because of the outside pressure?
So I guess it depends on sort of the key business factors that you have for your game. For a lot of mobile developers, I do think there's kind of starting to be a lot of pressure where a lot of people want to be playing more on the go, and it really is in your interest to, in that scenario, to use as little power as possible. And for a lot of people, it's going to be, are you willing to do the work to get the energy savings? If you can, you will actually see a benefit that other people are not getting because the compilers are actually not able to do this. So I would say it's a competitive advantage. Whether or not it makes actual sense for you depends on your specific game. Like I just showed in this example, even though I did the CPU optimizations, and for me it was a straightforward optimization, then I was saving like 4 or 5% battery per hour. For me, I'm seeing that being, oh, that's like a meaningful difference. For a lot of people, they might say, oh, that's not a lot. Maybe their GPU and like the phone screen being bright is taking up all the power, right? So they might want to focus there. But for me, just anything to make things go faster is a good thing. So
Right.
yeah, if you can figure out where it makes sense in your game, any of these techniques will pretty much always apply. It's all about making the thing go faster.
No, totally. And I actually want to get some perspective from Oliver and David on this as well, as you guys manage teams.
Yeah, one question that immediately jumps to mind for me is that object-oriented programming is very optimized to be understandable to humans, whereas SIMD immediately breaks your brain because you no longer have one thing that does a certain function, but you have chunks of things. So
Right.
how would you change the way you approach programming problems in your head to arrive at a SIMD solution?
Really, the biggest thing is being able to sort of think about how the CPU hardware is actually operating. That's the only way it sort of has ever worked for me. I'm not so sure it'll work for everybody, but for me, I always look at what is the CPU capable of, and I make the software do exactly what the CPU is capable of. And so from that, it's kind of how everything falls out naturally for me. But yeah, I agree. A lot of people, they have challenges because they're so used to the object-oriented programming mindset. The reason why that's harmful is because of the array of structs layout that I was illustrating earlier. Because you have these objects that are encapsulated and you don't know what's really in it, there's no way for you to control that actual data layout. You really want to sort of turn it inside out. You want to get all the data out there, put it in these nice arrays. Me personally, I've actually found that doing it this way is actually easier. The main problem is that there's lots of other code out there, even our own at Unity. Lots of APIs are like, here's an object, give me an object. And then you work with a component, right? Like, so because of that, if you're interacting a lot with the Unity APIs, that can be really challenging. You're always stuck in between the two worlds. So me personally, I spend all my time in this other world, which is not really object oriented, but you can often build a wall. Like so a technique that I've come across that I've used multiple times in different games is you have this really object-oriented code base and I want to do this SIMD optimization. You don't really need to change the whole code. Like what you could do actually is say that you have your list of objects and say they're all pointers, right? You're going to virtual function in to get some position or something. You just grab them all out from those original objects and create a whole new array. Just create it locally. Get all the positions, read them all out in one go. And then once you have the array filled out, then do all the SIMD processing. And then once you have your new results in the arrays that you know, temporarily created, you can then write the result back to each object. This is often a sort of middle ground. It's a step toward doing like the full optimal SIMD processing. And you will often win because you've paid all the cache misses at once in the beginning. And then you do all the quick processing with SIMD, and then you pay all the cache misses in the end. Whereas in the other version, if it's all object oriented, you might cache miss every single time you read something, and that might be way slower. So that's why this technique can actually still work. You know, you don't change all of your code. You just add this like, here's the SIMD bit that I'm going to do. That can actually work really effectively. So that's a good way to get a middle ground where you don't necessarily have to drop your object-oriented stuff. But yeah, you still need to do the mind change. That does just take a little bit of time and experience to do, unfortunately.
Yeah. As you're trying to do the mind change, are there signals or I guess how do you like best identify when to do that or when to implement it and when not to?
Usually for me, I'm looking at the code and being like, how many items? Like
Okay.
usually there's a loop and be like, how many
Yeah.
items is this loop going to process? You know, if we're talking hundreds, thousands, millions, SIMD for sure. If we're
Hmm.
talking like dozens and less all the time, it's probably not worth it. But once I know that I have like a really nice set, like this loop is going to process a bunch of data, I usually look at the content of the code. Are there lots of conditionals? If there are tons of conditionals in it, I'm going, I might want to not do SIMD here because it's not uniform enough. Um, but if there's only like one conditional and like the conditional, if you know the pattern of that conditional, like, oh, actually like 80% of all of the conditionals go through this branch, then you're like, okay, this is the uniformity is high. Like you always want to think about the uniformity. Is all of my data the same? Is there a lot of it? And is the decision that I make across all of these items, is it always the same decision? If it is, SIMD processing is like perfect. And that's sort of the key sense that you want to build uniformity. Is my data uniform? Um,
Mhm.
once you have that, most of the mind shift is in always thinking about all of these. The computation is essentially the same in every loop
Right.
iteration. If it is essentially the same, then you can just say, do it all at the same time for n number of items at once. In this case, mostly 4 times.
Hmm.
So that's usually the thing you want to keep in mind. Is each iteration actually different and doesn't depend on some other iteration? So if you have
Okay.
that, then SIMD is likely going to be applicable. Whether or not it's worth it, you need to see the uniformity.
Right. And then does the uniformity scale with the array size? Like if you're looking at arrays that are, 100,000 millions, will you accept higher conditionality
Um,
or
yeah,
like it's
I
like
can't.
5 conditions
Yeah.
and that's it?
So yeah, it depends. So if it's like there's lots of ways to deal with branches, but if it's actually
Mhm.
truly different for every single one, and you have to do like a logical, you have to switch to executing a different piece of code. In those instances, yeah, you really want to make sure that you have nice chunks. You know, if it's a different decision every element, SIMD is probably not going to win. But if you had like millions and you still have lots of those conditions, but they're actually all sort of contiguous. If they're contiguous, then that's not a real big problem. You can make your conditional check for all the items and then just do one huge chunk of code for that condition right there. So it's really about, is the data organized, basically?
Mhm. I think that's what it comes down to. It says. Okay.
And
I know we got about 15 minutes. I would ask, I don't know if David has any follow-ups before we open it up to the audience.
Yeah, would you, just a small one, would you recommend this like while behavior still changes of the code? Or would you say this is like the game is locked and loaded, now we're just wanting to make sure this runs on Switch or something, right? Like, where do you, in the production process, do you see this?
so yeah, it depends a lot. A lot of if you have like some fundamental foundational code, you can usually invest pretty early. If it's like core gameplay stuff that you know you're going to change all the time, it might not be worth it. It really depends on the structure of the rest of your code. So for example, on a game that I like one of my first games that I ever worked on, like almost all the code I was like trying to do SIMD. And at first it was really tough because it was like, oh my gosh, I feel like I'm fighting against the grain. But it was because I didn't write enough of my code where everything was in flat arrays. Like once you do enough of it, you'll reach a critical mass where it's like you can write all your code this way from the beginning. But I don't think that's like a common, I don't think most people will be able to pull that off. You really do need to know the CPU pretty well, and you have to be pretty experienced in this way of processing things. So I would say really what you should do is like you should try to ramp up. You know, don't just jump into the deep end. So yeah, for gameplay code, I tend not to do this sort of thing. I focus more on algorithms and higher level optimizations. So if I know that like A star is taking a while, I don't think I'm going to SIMD process my A star pathfinding. What I'll probably do is figure out a way to like time slice my pathfinding or do a small chunk, you know. So in gameplay, it tends
Yeah, that makes sense.
like so I would say for most people that do this sort of thing, they usually wait until the last few months of like before like when they're about to ship the final version. Oh, we really need to make this thing fast. That's usually when people go for the SIMD stuff. You really want to be able to write the code and sort of depend on it for like at least a few months, you know, not just a few days or weeks.
No, totally. That, you know, where could you point folks to learn more about SIMD, like tools and resources, besides obviously your wonderful talks,
Yeah, yeah.
just so they can, brush up on it?
Um, so I mean, the ultimate place, of course, is the CPU hardware manuals, which for me is awesome, but those things are monsters. I would say there's lots of other great talks on SIMD. Another good one that I know about is from a guy named Andreas Fredrickson. He's at Insomniac. He's done previous presentations on SIMD processing. Um, Great presentations, and it's a really good starting point. Um, I think honestly, it's kind of stuff that the game industry has managed to generate, but SIMD processing is getting more popular. There might be a CPP con talk out there. I don't quite remember. I'd have to look that one up, but I think it's mostly going to be presentations from folks like us
Oh,
from the
cool.
game industry. Yeah,
That's great.
I can share a link later, and then people can find the presentation I'm talking about.
Cool. All right. With that, I think we can open up some questions from the audience. We don't have any in the chat, so uh,
Okay. Oh, is that a question right there?
yeah, you want to read it out loud so we can.
Sure. You mentioned measuring SIMD differences you showcased on your phone with a native profiler. Is that a rough estimation of the data you gain there, or is there a precise number you can, or a precise number you can trust? All right. I'm trying to understand the question. So it sounds like, is the profiling, like data that I got from the native profiler, is that accurate? If that is the case, I guess it's accurate statistically speaking. Oh, for the power consumption. Yeah, power consumption, that's an interesting topic. So through my time at Unity, what I've discovered is that any power numbers that you get, they're almost always estimates.
Mhm.
My understanding is that Apple's Power Profiler, the estimates are actually reasonably accurate. If you're seeing a couple of percentage points difference, it is likely that it is actually truly a difference. But again, it's an estimate. The reason why is unfortunately a little sad. Is with phones in particular, the reason is sad. The on phones, there is no hardware that measures the actual power going through the circuitry. They don't want to spend the extra few pennies or whatever on the millions and billions of phones that they're producing because that will add up. So it all ends up being this heuristic. I don't know actually how they do it. My understanding is that the Apple devices tend to be pretty good. Android is a little bit harder, but the numbers are supposed to be usable. What
Mhm.
I would say is the ultimate the ultimate source of truth is how long did the phone stay on when you were playing the game? So in practice, what I find is that developers end up literally doing that. They charge up to 100%, and then they run their game in some unlimited mode, and then they just time how long it takes for it to turn off. And unfortunately, that is the situation there. If you're on like a plugged in like situation like desktop PC, um, you can always bypass the profiler entirely by getting like a power meter and then just seeing how many watts you're using. So that's actually what I end up doing a lot of times when I'm doing these power optimizations. I'm actually on desktop where I can plug in this power meter and see, that's the wattage that I'm pulling right now.
Quick follow-up question. Why would you not do the same for the mobile phone? Can you not plug in your mobile phone to your wall to charge it, but then put a power meter in between?
So I believe you can do something like that, but I've been told by several people because of the way that the power circuitry works in the phones, that can change a lot of the performance characteristics. So they're like, if you want to see what the user is going to
Yeah,
see, they're probably not going to be plugged in. So yeah, that's the main reason. But I think in principle you could do that, but the
yeah,
phone does this weird thing of like when it decides to charge. So like you don't really know. Oh, I think we've got.
yeah. From my understanding, I think the phone will go to the battery first, and then the battery goes to the wall. So it might not be the same energy
Yeah,
follow curve.
yeah. I mean, like over a long period of time, I'm sure you can average it and see it, but it's
Yeah,
it's not quite the same
you
as
won't
the
see the
plugged
same
in
peak.
situation. Yeah.
Yeah.
All right. Okay.
Nick has his hand up. Yeah.
Right.
Yeah, I'm just wondering, sort of also profiler related, like if you're looking in the Unity profiler, is there a particular heuristic you're using to say like, okay, like I mean, you know, sometimes like code is just heavy code or whatever. Is there
Right.
something you use, mentally just to be like, okay, this is probably a region where like it's heavily algorithmically intensive, as opposed to some other.
Right. I mean, just from the Unity profiler is pretty hard because you just see
Yeah.
like the
Okay.
profiler markers and it's like, oh, X number of milliseconds.
Mhm.
Um, in the Unity profiler situation, it's like I'm comparing it with like lots of the other work. And usually I'm just looking for
Mhm.
the biggest profiler marker
Biggest chunk. Yeah. Okay.
that's like in your code usually,
Mhm.
right?
Yeah.
Um, that's usually as much detail as you can get, and that's usually good enough. But yeah, if it's like an algorithmic thing, you definitely have to get in the code and understand it a little bit to see what the algorithm really is.
Yeah. Okay.
So you almost always need to do like Unity profiler plus something else that gives you source level profiling
Mhm.
information.
Okay.
Yeah.
All right. Thanks.
Anything else? And so another benefit that I just want to point out here that's often not clear. Um, a lot of people see the SIMD stuff as being like a really challenging optimization, but actually, for me, it's like a stepping stone. SIMD is not always the final destination, but the thing that I was mentioning is having your structure of array layout. If you have that, that opens the door to lots of optimizations. So if you can do SIMD, that also means that you can parallelize. You won't have to synchronize because SIMD kind of requires independent pieces of work. If you have the independent pieces of work and you could do SIMD processing on it, that means you could have just done, a parallel for job in the Unity job system. So often the work of you just doing the data rearrangement makes it easier to do other optimizations. And if you compound those optimizations, you're gonna be like 100 times faster, like 100 times faster is like huge. So even though it might seem like a lot of work, it could still end up, you know, benefiting in the end because you can do two or three different optimizations with this.
Well, that's great.
Awesome. Dale, thank you so much. I mean, yeah, I really love this stuff because yeah, I think energy efficiency is really, really important, and I'm really happy of getting more and more best practices and examples out there. Because yeah, I think if we just have like more people using this stuff and trying it out and showing what it can do for the games and the player experience in the end,
Right.
I think there will be more people using it. Especially like there are so many people spending so much money keeping players in their games, but then they
Right.
run out of battery. So I think even 5%, like yeah, longer playtime can make a huge difference. So yeah, thank you so much. I will quickly still post the link to our next meetup, which might be interesting for the audience here. Um, okay, yeah. Yeah, there is another comment on yeah, bad reviews because of battery usage. That a game,
Yes.
yeah, exactly. So it really affects the player experience. Um, Yeah, thank you so much, everyone. Thanks to all the speakers and participants. And yeah, would love to have you with us next time. Thank you,
Awesome.
guys.
Thank you so much.
Thanks, everyone.
All right. Bye-bye.